for me, but hopefully I can hold your attention for the last 12 minutes and bring us home. So this is my third and final year as a Hubble Fellow. So of course, thank you to the leads for organizing throughout the years. It's been a really wonderful 2 years, and I'm very excited for this last year to see what I can produce. Thanks also to the fellows who volunteered to volunteered their time to help organize the symposium as well. This is my last symposium, but the first one I've been able to attend in person. So it's really nice to finally get out here and experience it in real life. So yeah, today I'm going to be talking about this project, scuba diving for JWST faint dusty galaxies in our first Cosmos Web release. I think we all know one of the great things about having one of these independent fellowships is the ability to just kind of like go down rabbit holes and see whatever little projects where they may take us. So I'm going to just tell you a little bit of a story of one of those projects that came about in the last year. And so, wrong button, not arrow, click. Okay, nope, also not click.
Oh, you're at the last slide.
Oh, that, okay, that's why. I was like, arrow works, okay. Can I remove this too? No, I can't.
Yeah,
You're on the side. Oh, there you go. One of these days we'll get Zoom right. Okay. So the reason I was able to kind of go off on one of these little side projects had to do with data acquisition. I primarily work in the Cosmos collaboration. We have this huge Cosmos Web JWST survey. This is a 255-hour treasury program covering half a square degree with NIRCam imaging. And when you have a survey this big, you are not going to get it all at one time, right? And so if we actually color code these pointings of JWST imaging by when we actually were supposed to observe them and get the data, it broke down into these three main chunks. And for reference, the millimeter data set that I primarily work on is located in this top right corner of the blue area. And so as you might be able to guess, if you actually look at the dates of this data, the red chunk was the first chunk we got observed, and we got the data in January of this year. The green southern half was our most recent data acquisition in April. And of course, the data that I actually really cared about that covered my millimeter survey is not going to be observed until December. So I had a little bit of time to work on some smaller side things while waiting for this data. The bane of any observer's existence is waiting for data to come in, right? So the story begins also with my friend and colleague, Dr. Jed McKinney, who is now a postdoc at UT Austin, who back in January was getting ready for his AAS talk and just looking through that first January chunk of data that came in, trying to find something cool to include in his AAS talk. And so we often try and like play around with the data, just see what pops out. For a millimeter astronomer looking at dust continuum emission, the first thing you might do is just plop some millimeter contours down on your new optical or near-infrared data and see if any of the objects overlap, right? So Jed found a source that he thought seemed interesting, and he kind of asked me about it. So this is the kind of serendipitous rediscovery of an object called Aztec 71. So this source was found by the Aztec millimeter instrument, but had no wavelength coverage shortward of 850 microns. So because of that, it's mostly left out of, catalogs and surveys because there's no optical data to kind of constrain the target at all. But he showed it to me and asked, like, do you think this is a reasonable thing to try and publish as a single source paper? And I said, heck yeah, this has the potential to be the highest redshift unlensed dusty star forming galaxy, and one of the earliest ones to have JWST data now. So Jed went ahead and led that work. And the source ended up being broadly similar to these other known optical and near-infrared dark galaxies, which is the type of galaxy that I spend basically every day thinking about. But some of the basic properties of Aztec 71 ended up being the photometric red solution was very high at 5.7, booming far infrared emitter, large dust reservoir, and undergoing extreme burst of star formation, right? So just a brief primer on these kind of near dark galaxies, as I call them. So this represents a subsample of the dusty star forming galaxy population at high redshift, so redshifts greater than 3 or so, and that are being more readily discovered now that we have more ALMA surveys coming out, and now with JWST that'll help even more. So an example of one of my near dark sources is the cutouts at the top. You see there's no detection out until through the K band, and then once you get into the IRAC channels and beyond into the submillimeter and millimeter regime, then you have a clear source detection. There's also been serendipitous detections of these near dark galaxies. So the other plot is showing an example from the Rebels program where they were targeting the very middle yellow point in the HST data, but then they also found this near dark galaxy just above it that shown very brightly in the ALMA millimeter contours. This near dark status is still very kind of up in the air. It's a very purposely vague term because we still know very little about these galaxies and the various galaxies that might all have this near dark status. We think it's likely dependent on some combination of their redshift and their dust geometry. So you can imagine if you have a galaxy where all the dust is nicely laying over your young stars and absorbing all that UV emission and putting it out, then you're not going to see any rest frame UV emission. Maybe that's patchy though, and you get some leakage, and then it's not near dark. So that's something we're still very much trying to sort out in terms of why these galaxies are appearing this way. The other thing to keep in mind is that different names are used throughout the literature, depending on wavelength coverage and survey depth. Oh, Cal's like 1 minute, dang, okay, 5 minutes. Thanks. Right, so we have a lot of work to do of sorting through these different kind of surveys and what they're all probing, right? But the thing that's kind of important here is that of the broader dusty star forming galaxy population that we know of, about 25 to 35% of them have been found to be near dark. So if you're looking at optical or UV based surveys, this is just a huge portion of galaxies that you are missing completely. And there's still a lot to learn about dust production in the early universe, dust obscured star formation in the early universe, just how much is out there. Okay, so if you're curious about my title and why it's called scuba diving, that has to do with just the fun name we came up for this kind of one-off project. And so Jed asked me after he found that first source if I thought any more might exist within that small January chunk of the JWST data. And just thinking about what I know about number densities of near dark galaxies, I thought maybe one, but I wouldn't be surprised if maybe there weren't any. So he asked me if I wanted to go ahead and look for more. And I said, sure, I've got a little time. So this is our scuba diving approach. This is our selection method for trying to find more galaxies like Aztec 71. So that starts with the Scuba 2 survey. So this is an 850 micron wide survey that covers all of the cosmos field. And so the first step is just to look for sources, robust sources, so greater than 4 sigma, that fell within that January Cosmos web release. The second part, which is the real limiting factor here, is to search for high resolution millimeter counterparts in the ALMA archives. So if you don't know, the Scuba 2 beam is like 15 arc seconds wide. There's a good chance you're going to get multiple sources falling in your beam. And so you need the high resolution counterpart to then match to the JWST counterpart. And then, yeah, so then you want to match those positions and find the correct JWST object that that is emitting the millimeter emission, right? So what that ended up being was there were 30 sources from the first step down to 13 sources in the second step, and a final sample of 8 sources that had the ALMA positions and the JWST coverage. So this is my in-prep work that I hope will be out soon. So of these 8 objects, 4 of them in particular were very interesting to me, as they are the most similar to Aztec 71, and they were not included in our last huge Cosmos catalog, which is a K-band selection. So, and so you can even see that these are all 1.5 micron dropouts. That's the second panel. You don't see anything. The second object actually is a non-detection in 2.7 microns as well, which is very cool. But broadly, they all share kind of similar properties as well. All their photometric redshifts, but then redshifts greater than 5. Again, whopping far luminosities, large stellar masses, and huge dust reservoirs of 10 to the 9 solar masses. So there's a lot of questions of how do we build up all that dust within the first, 2 billion years of the universe. Okay, so in the past, I've always started from the millimeter regime and then worked my way out into other wavelengths. But now that we have the JWST data in hand, there was a question of, can we now select for these highest redshift, dustiest galaxies from the JWST photometry alone? And it looks like signs point to yes. So here's a color magnitude plot of those scuba dive sources are the blue circles. And then I've plotted everything else that might be an interloper or get in the way of my sample. So the beige triangles are more classical submillimeter galaxies. Those are brighter and usually maybe a little lower redshift. We have a quiescent galaxy sample in the red. And then the high redshift candidates, so redshift greater than 9, kind of normal galaxies in the green. And it just based on this kind of preliminary plot, it seems like the near dark galaxies do occupy this kind of distinct parameter space in this diagram. So that is a cool thing to think about, starting from the JWST catalog and then maybe looking for millimeter follow-up afterwards. I will just point out, so I work primarily now with the MORIS survey. So this is mapping obscuration organization with ALMA. This is our 2 millimeter survey that was in that top right chunk of our JWST data that we don't have full coverage for. But MORA did overlap a little bit with this. And it was thanks to MORA that we got most, or like 40% of the millimeter high resolution counterparts, and without this MORA data we would not have been able to do our scuba dive sample basically. So wide area searches in the millimeter are super key, because like the ALMA coverage in Cosmos is like 5% or something, so we just don't have the millimeter coverage. So this is a go wide area millimeter searches, but unfortunately ALMA is not the best tool for this. So in the future, we'll soon have the full Cosmos Web area, but again, this lack of millimeter coverage will be the limiting factor. We luckily had some great success in ALMA cycle 10. We're going to get snapshots of about 500 scuba sources at 870 microns. There's also this CHAMPS program that's doing 1.1 millimeter survey covering all our NIRCam plus MIRI coverage that we have in Cosmos Web. So again, this is like kind of illustrating our issue here with just the scuba data. What source is actually emitting or causing the emission? Multiple, who knows, right? So you need that high resolution millimeter data. But as I said, ALMA is not really actually a map maker. One of the main reasons I went to UMass Amherst was to use the large millimeter telescope, specifically the Toltec instrument, which does simultaneous 1.1, 1.4, and 2 millimeter mapping. And so I PI'd this program to look at this cluster field, which I'm waiting on the data for that as well. But just to kind of drive the point home, this 6x6 arc minute map can be done in a little over 3 hours with Toltec, and this would take 30 hours with ALMA. So if we want to do large swaths of sky, I'm really excited about the future of Toltec. I'll just say, I think a lot about near dark galaxies, and what we really need to do now is work on figuring out, we're just really building up the census still, but we have to figure out what's going on in these galaxies, how they might break down. This is just showing on star formation rate over stellar mass. It's like just this continuous distribution of all the near dark sources that we know of currently. Some of them have radio, some of them don't, it's a big mystery at the moment of why some are certain ways and some are other ways. Okay, so I'll just leave it my summary and happily take any questions.
I was wondering why it's important that you mentioned earlier in your talk that it's important that the very first galaxy discovered was online.
Oh, yeah. Yeah, right. Just if they were lensed, you could potentially go to like higher redshift things, but if you're looking at blank field surveys, you're not expecting to be in, you don't want to be in a cluster, right? So just without any boosting necessary, this is the highest redshift that we've been able to find. And so it's just a matter of trying to figure out these time scales of what are the earliest galaxies possible. So there are like, I want to do a cluster survey as well to see if we can even go deeper and farther. But yeah, that was just a fact that a lot of people ask when I say, oh, it's a redshift 5.8. They say, is that lensed? I was like, no, it wasn't.
Brandon,
Awesome talk. These are such cool galaxies. I was just wondering what the resolution of Toltec is. So like how well can you do the localization at?
Yeah, so the shortest wavelength is still 5 arcseconds. So depending on how crowded your field is, it could be easy to pinpoint the source. But yeah, that's still something to consider. You can also couple it with radio observations to really nail it down. But again, some don't have radio, some do. Why is that?
Hi, I'm not too familiar with Scuba 2. Do you have any variety information for even just a small sample of local bright galaxies, or can you do variability with Scuba 2? Like, do you have it just for free in your data sets?
Oh, potentially. That's not something I've thought too much about, but there's tons of Scuba 2 data, so it's all readily available.
Okay, that's all the time we have for questions. Let's thank Sinclaire again.